first going to start talking about bond strengths. You know that we have been drawing these energy interaction curves as a function of R. And we have defined here a bond energy, a bond dissociation energy, E sub D, as that energy difference from the bottom of this well to the separated atom limit. And let me consider the separated atom limit now to be a separated methyl group and a hydrogen atom, because I want to talk about the CH bond. Okay? So this is the bond dissociation energy for CH in methane. All right, but now what we're going to do is we're going to change our definition a little bit. Instead of talking about an energy, a dissociation energy, a bond energy, we're going to talk about a bond enthalpy. And I'm going to represent the bond enthalpy by delta H. It turns out that in the laboratory, we can more easily measure a delta H, a bond enthalpy, rather than a bond energy. We can do so because most of the experiments we do are at constant pressure. When we do an experiment in the lab, that's at constant pressure. And the relationship between delta H and delta E is the following. Delta H is equal to delta E plus delta PV. All right? Now, where this relationship comes from is a subject of a great discussion in 560 in chemical thermodynamics. You will see that if you take 560. At the moment, we're just going to take this as a given. But I'll tell you that although delta H and delta E differ, for gases, the difference is on the order of 1%, 1 to 2% for gases between delta H and delta E. They're both an energy, but we're going to call it an enthalpy. All right? That's actually what we measure typically in the laboratory. For solids and for liquids, the numbers are essentially the same, right? But for gases, there's a 1 to 2% difference. So if you're doing an exact calculation, or you really do need to know that number exactly, you need to get the bond enthalpy. And in fact, if you go and you look up bond strengths, they will, for the most part, all be bond enthalpies and not bond energies. Okay, there's a more extensive table of bond enthalpies than there is for bond energies. Okay, so we're going to start talking about delta H for a bond now. All right, and in thermodynamics, as again you'll see in more detail in 560, in thermodynamics, we always need a standard state. We're always going to be, for the most part, measuring things relative to one another. And so we need a common ground. We need a standard state. And what your book uses and what most people now use for a standard state is the pressure 1 bar. So the standard state really refers to the pressure, and actually not the temperature. But 1 bar, right, is equal to 10 to the 5 pascals, right? And a pascal is a kilogram meter per second squared, 10 to the 5 kilogram per meter second squared. And the relationship between bar and atmosphere is 1 atmosphere is 1.01325 bar. All right? So an atmosphere is 1.01325 bar. I'm sorry? Okay. And so to represent this standard state here, we're going to put a naught up here. We're going to put a superscript up here. This is going to be delta H naught. That's going to represent our standard state. Okay? Okay. So why are, all right, and so on the first slide here, that's what we'll do now. I think that's right. Okay, on the first slide, here, what I've got are a bunch of bond enthalpies. And these are bond enthalpies for, all of them are for CH bonds. First one is for the CH bond in methane. Second one for the CH bond in ethane. Third for the CH bond in CHF3. And what you can see is that they're all about 400 kilojoules per mole. They're not all exactly the same, and they shouldn't be. They're different molecules. The bond strength really does depend on the individual molecule, but they're all, roughly speaking, the same. And so what is often done is to take bond enthalpies such as this and average those strengths over many different molecules for the same bond so that you have an average bond enthalpy. And that's what you'll see plotted, or that's what you'll see a graph of. This is a table from your book that gives you the mean bond enthalpy for example, CH bonds, 412 kilojoules. Gives you the mean bond enthalpy here for CC bonds, 348 kilojoules. For carbon-carbon double bonds, 612 kilojoules. All right? And so those are the kinds of tables that you'll often see. But remember, these are average bond enthalpies. They're going to give you that bond enthalpy approximately correctly, but not exactly correctly. And that's going to be important, as we're going to see in just a moment. Okay. Now, why in the world are bond enthalpies important to us? Well, they're important to us because they determine the enthalpy of a chemical reaction, right? If the bond enthalpies in a product of the reaction, if those bond enthalpies are stronger than the bond enthalpies in the reactants, well then the enthalpy of that reaction is going to be negative. You're going to have an exothermic chemical reaction. If the bond enthalpies in the reactants are stronger than those in the products, well then we're going to have an endothermic reaction. So the bond enthalpies, the relative bond enthalpies, are going to determine the sign of the enthalpy of the chemical reaction. So let's look at this reaction here. Very important reaction. This is the oxidation of glucose. Very exothermic reaction, minus 2,816 kilojoules per mole. Hey, this reaction is going on in every single cell of your body. It is this reaction that you are using right now to maintain your body temperature, to move your muscles, to repair tissue, to think, right? This oxidation of glucose is important. I mean, this is the reaction, and this is the reason why we eat. This is the reason why we breathe. This is the reason why we exhale, and this is the reason why we pee. Okay, so what do we have to do to calculate the enthalpy for this reaction? Well, what we got to do here is got to take glucose, and that's the structure of glucose, blood sugar, and that of oxygen, and we have to calculate how much energy it's going to require, how much enthalpy it's going to require to break every single one of these bonds in glucose. So what we have to know is how much energy is required to break 7 CH bonds. All right? We have to know how much energy or enthalpy is required to break 5 OH bonds. Here are our OH bonds. And how much enthalpy is required to break 5 CO bonds. Here are CO bonds. And to break 5 carbon-carbon bonds. And to break 1 CO double bond. And then finally, we need the enthalpy to break 6 molecular oxygen bonds. Okay? So, we can calculate that, right? We can calculate the enthalpy to break all of these bonds by looking up the values from that table that I just showed you, the table of average bond enthalpies. And when we do that, we find it's a whopping 12,452 kilojoules per mole. That's what we're going to need to take glucose and oxygen to the elements, right, the atomic species. All right. Well, then likewise, we know that although we need to put that much energy in to break the bonds, we're going to get some energy back when we make the bonds, right? So now we need to know how much energy, enthalpy, we're going to get back when we make 12 CO double bonds and when we make 12 OH bonds. And again, we can use our table of average bond enthalpies to calculate that when we make those bonds, we get 15,192 kilojoules of energy or enthalpy back. And then the difference between this, right, this energy and that energy, well, that is the enthalpy of that reaction, minus 2,740. Okay? So what did we do here? Well, what we did to get the enthalpy for the reaction is we took the bond enthalpies for each bond of the reactants, and we summed them all up. And we took the bond enthalpies for each bond of the products, and we summed them all up. And then we took the difference, and that's how we got this number, minus 2,740 kilojoules per mole. All right? Okay, but now what I want you to notice here, and this is important, what I want you to notice is that we calculated these enthalpies by taking the enthalpies of the bonds of the reactants minus those of the products. When we measure enthalpies for chemical reactions using bond enthalpies, it is reactants minus products. The reason I tell you this is because in a moment I'm going to show you another way to calculate the enthalpy for a reaction, and that way will be products minus reactants. All right? So you got to keep this straight. This is reactants minus products. All right. But now you see that I just calculated a number for that reaction enthalpy of minus 2,740. And the experimental value here was minus 2,816. Some of you are looking at your notes like it's not in your notes. Is that right? It's in the notes. Okay. All right. Okay. So, gee, you know, this is what I told you was the experiment. This is what we calculated would happen here, right? Well, remember that what we used to calculate this number was average bond enthalpies. We didn't use the exact bond enthalpies for every bond in every bond that we had. And there's a difference. And so how can we calculate this in a more accurate way? I mean, sometimes, depending on what you're doing, sometimes it's okay to have the average bond enthalpies. You're close enough. It's good enough. Sometimes it isn't. So when it isn't, what can we do? Is there a more accurate way? Well, you could have the exact bond enthalpies. But you know, the bottom line is that if you had the exact enthalpies for each bond, for each known molecule, can you imagine the table of numbers that you would have to have? Right? In fact, such a table doesn't even exist. I mean, just for glucose alone, right, we would need 23 different numbers, 23 different bond enthalpies. That is a large amount of data that we would need to do this exactly from the bond enthalpies.
Can't we fix a robot to do these kinds of work?
I'm sorry?
Can we fix a robot and program it and put in data?
Absolutely. That's your job, okay? That's why you're here, to sit in class and say, gee, that's too hard, let me think of another way to do it, okay? That's what an MIT education's all about. Okay, I'm serious. You're okay, all right. But we do have a less cumbersome way to handle this, and that is using heats of formation. Okay. So a heat of formation, what's that? Here it is. I'm going to define this as delta H naught sub F. That's a heat of formation. It's an enthalpy. It is the enthalpy of a reaction that forms 1 mole of a compound from the elements in their most stable form in the standard state, which is 1 bar pressure here. All right. Let me explain that. Here's a reaction that produces 1 mole, that's important, 1 mole of liquid water. The enthalpy for this reaction is minus 285 kilojoules per mole. Right? That enthalpy here is defined as the heat of formation for water, because the enthalpy for this reaction forms 1 mole of water, and it's forming 1 mole of water from its elements. But the elements here are in their most stable form. The most stable form of hydrogen that makes up this water here, the most stable form at 1 bar pressure and at room temperature. And I forgot to tell you that I was going to talk about delta H's at 298.15 degrees Kelvin. Okay, all of our delta H's will be for that temperature. Delta H does depend a little bit on temperature, but we're not going to do that here. We're going to do that in 560. All right? So 298.15 is the temperature at which you're going to be dealing with all of your delta H's. But anyway, H2, that's the most stable form of hydrogen. And then oxygen here. Well, that makes up one of the elements in water. And so the most stable form of oxygen at this temperature and pressure is indeed molecular oxygen. And so this equation satisfies this definition, forming 1 mole of a compound from the pure elements in their most stable form. All right? Let's look at this reaction. Here we're forming 1 mole of oxygen. And we're forming it from 1 mole of oxygen. The delta H for this reaction is a whopping 0. However, this is the definition for the enthalpy of formation for oxygen, because we're forming 1 mole of oxygen from its elements in their most stable form at the standard state. The most stable form of oxygen is oxygen. All right? So the heat of formation, the enthalpy of formation of molecular oxygen is 0. Such is the case for the heat of formation of hydrogen, H2, or nitrogen, N2, or chlorine, Cl2. All right, Cl2 gas. The heats of formation of those compounds are all equal to 0 because they're in their most stable form at 1 bar pressure and temperature and 298 Kelvin. What about this reaction? Well, this reaction here it's forming 1 mole of glucose. It's forming 1 mole of glucose from glucose's elements in their most stable form. Here's the hydrogen, molecular hydrogen. Here's the oxygen, molecular oxygen. And here's the element carbon in its most stable form. And you see this GR? That stands for graphite. The most stable form of carbon is graphite at this standard pressure and this temperature, 298 Kelvin. All right? So the enthalpy for this reaction, minus 1,260, that is the heat of formation, or the enthalpy of formation for glucose. All right, so now we looked at the definition for the heat of formation. How are we going to use the heat of formation to calculate the enthalpy for a reaction? That's what we're going to do now. All right. So here is our reactant, or here are our reactants, glucose and oxygen. What we're going to do is we're going to use the heats of formation to calculate how much energy we need to produce the elements of glucose and oxygen, the elements in their most stable form, meaning graphite, molecular hydrogen, molecular oxygen. That energy here is minus the heat of formation of glucose, because now I'm taking this reaction and I'm going backwards, right? I'm going from glucose to the elements. So this is going to be minus the heat of formation of glucose. It's going to be 1,260 kilojoules. But then what I'm going to do is I'm going to form the products. I'm going to take the elements in their most stable form, put them together to form the products. So in this case, I'm going to form here 6 CO2 molecules. So I need the heat of formation of CO2. Since this is per mole, we got 6 moles of them. It's minus 2,361. And then I'm going to take these elements and form the other product, water. And there's 6 moles of water. So I need the heat of formation of water times 6 minus 1,715 or something. And then the difference between the sum of these two energies and these energies, well, that's the enthalpy of the reaction, minus 2,816. That's a tabular or energy diagram form. We can also write out the equations. Let's do that. All right, so here's the reaction that defines the heat of formation of glucose, except I wrote it backwards. Right? This is glucose going to its elements in their most stable form. The enthalpy change for that reaction is minus, now, the heat of formation of glucose. Here's the reaction that defines the heat of formation of CO2. The enthalpy change for that reaction is 6 times the heat of formation of CO2, because we got a 6 here, right? The heat of formation is for 1 mole, but now we've multiplied this whole equation by 6, so we need to multiply that by 6. Then we've got an expression here for the formation of 6 moles of water. So the delta H for that reaction is 6 times the heat of formation of water. And now we're going to add them all up. We're going to add up the reactions first. And what you can see is that there's going to be a lot of cancellations. We did this correctly. Hey, this 6 carbon atoms in the form of graphite is going to cancel with this graphite on the left-hand side. This 6 moles of H2 is going to cancel with this 6 moles of H2. These 3 moles of O2 are going to cancel with these 3 moles of O2. And then the 6O2 cancels with this 6O2. We add them all up, and we have the reaction that we're looking for, the oxidation of glucose. And then, of course, we're going to have to add up the delta H's for all these reactions. when we do so, we get minus 2,816. That's the enthalpy change for this reaction. What I just did here, adding up these reactions and the corresponding delta H's for these reactions, well, this is an example of Hess's law, which I think you've seen before, which says that if you have two or more chemical equations that are added up to give another chemical equation, that's what we did here, right? You then also have to add up the corresponding enthalpies to get the enthalpy change for the overall reaction. Okay. So now, what did we actually do? I showed you how to calculate the enthalpy for this reaction, both in kind of this graphical form and also kind of this mathematical form where we wrote out the equations. But the essence of what we did is this. What we did is we took the heat of formation of each one of the products, multiplied it by the appropriate stoichiometric number, and then summed over all of those heats of formation. And then we took the heats of formation for each one of the reactants, multiplied it by its appropriate stoichiometric number, summed over all of that, and subtracted the two to get the enthalpy for the reaction. So for glucose, right, we took one product, CO2, multiplied that by 6 for the heat of formation, added to the 6 times the heat of formation of water, subtracted from that the heat of formation of glucose and that of oxygen, and then that is our calculated value for the reaction. And indeed, that does agree with the experimentally measured enthalpy for the oxidation of glucose. Why? It agrees exactly because we use the heats of formation. The heats of formation are specific for the individual molecules that are participating in that reaction. It is exact, right? And having tables of heats of formation is certainly the tables are much less extensive than what you would need for the bond enthalpies for every bond in every known molecule. All right, and so these tables of heats of formation are readily available to you, and you can get exactly the enthalpy for the reaction. Okay? But now, the second very important point here is look at how we calculated the enthalpy for this reaction. We took the heats of formation of the products and subtracted them from the reactants. In the case of getting enthalpies for chemical reactions from the heats of formation, it's products minus reactants. All right? For bond enthalpies, or for getting the enthalpy of reaction from bond enthalpies, it's reactants minus products. You can be sure to see this soon, like on November 2nd, all right? Something you want to remember, something you want to know. All right, questions on that? All right, this is important. Okay, and I just want to make one other brief point here about delta H's and many thermodynamic quantities, but delta H in particular here, and that is that delta H is a state function. That means it's independent of path. So for example, here I've got glucose decomposed to the elements, not in their most stable form, but glucose decomposed to the elements, and then rearranged to form CO2 and water. The difference between this energy and this energy is the enthalpy of the reaction. And we calculated the enthalpy of the reaction in this way if we had used exact bond enthalpies. But we also calculated the enthalpy using the heats of formation, taking glucose to the elements in the most stable form and then recombining them. Again, the energy difference is minus 2,816. What this is an example of is the function enthalpy being a state function. It's independent of the path that we took to calculate it. We can go up here and then come back down here. You're going to get the same number as you go up here and come back down here. That's what we mean by a state function. Again, you'll talk about that in more detail in 560. Okay, so now we have, that takes care of enthalpies for the moment. And what I want to talk about is another concept. And I want to talk about spontaneity. All right? And spontaneity, or spontaneous change, is certainly something that you're familiar with. Right? It occurs by itself without any outside intervention. It has directionality. So, for example, if you put a rock near the top of a hill and you let it go, you know what's going to happen. It's going to roll down. It's not going to roll up. All right? That's a spontaneous process. If you have a gas, say over here, right? You have a gas at high pressure and then a stopcock and a bulb here with a vacuum, and you open the stopcock, you know that that gas is going to flow from high pressure to low pressure. It's not going to go the other way. That's a spontaneous process. You know that if you put a hot object next to a cold object, the heat is going to flow from the hot object to the cold object. It's not going to go the other way. Right? However, although a change might be spontaneous, it may not be fast. If you take a bottle of ketchup in the days when the bottle of ketchup was a glass bottle and you couldn't squeeze it, right? You turned it upside down, well, the ketchup has a spontaneous tendency to come out, but it may not be fast. Right? So what we want to understand is what is the key to spontaneity, in particular for chemical reactions. So for example, you know that iron rusts, and you don't have to do anything about it to make it happen, right? It rusts. Turns out that iron rusting is a very exothermic reaction, minus 824 kilojoules per mole. You know that if your stomach is a little bit acidic, that as long as you ingest something that is basic, that you can neutralize that acidity. That's also a very exothermic reaction, minus 56 kilojoules per mole. Another reaction that occurs in every cell of your body is this transformation, or the reaction of adenosine triphosphate, the hydrolyzation, the reaction with water, to adenosine diphosphate. This also is an exothermic reaction. You don't have to do anything to make it go. It goes. So the question is delta H the key to spontaneity? Well, let's look at this reaction. This reaction is ammonium nitrate dissolving essentially in water to make ammonium ion and nitrate ion. And the question is this reaction spontaneous? I mean, this is a reaction that's about 24, 25 kilojoules per mole endothermic. So does an endothermic reaction happen spontaneously? Well, to answer that question, we're going to have to do a, this is a hot pack. Okay. We're going to have to do an experiment. And the experiment we're going to do is with one of these cold packs. And we're going to carry out this reaction. We're going to see if it's spontaneous. So what you're going to do is, and the TAs can give out a few of the cold packs, what you're going to do is you're going to take a cold pack and you're going to find the little piece, the little packet inside this cold pack that has water in it. And you're going to squeeze it to break that packet. And then you're going to see if this reaction goes. If it goes, hey, it's going to get cold because this is an endothermic reaction. It's going to pull heat out from the environment. All right, and some of you should have gotten hot packs. All right. Is an endothermic reaction spontaneous? Yes. Is an exothermic reaction spontaneous? Yes. Is delta H the key to spontaneity? No. Okay. So it's not the key to spontaneity. What is the key to spontaneity? What is the key to spontaneity? Delta G. That's the key to spontaneity. The Gibbs free energy. There it is in all its glory. Delta G is equal to delta S, delta H minus T delta S. Okay, what's delta S here? Delta S is the change in entropy. What's entropy? Entropy is a measure of the disorder in a system. So if you have a positive delta S, if the change in delta S, if the sign of delta S is positive, you're going to have an increase in disorder. The system's more disordered. If you have a negative delta S, if the change in delta S is negative, you're going to have a decrease in disorder. That's going to affect delta G. It's not just delta H, but the change in delta S is going to affect the spontaneity for a reaction. And so the combination of delta S and delta H is this delta G. And our conditions for spontaneity are the following. If delta G is less than 0, then you have a spontaneous reaction. If delta G is greater than 0, then you have a non-spontaneous reaction. And if delta G is 0, hey, then you're at equilibrium. All right, so these are the conditions for spontaneity. These are the conditions under conditions of constant temperature and pressure. This is also important. We won't dwell on this. And the actual origin for these conditions is something, again, you're going to talk about in exquisite detail in 560. Okay? But let me try to give you a feeling here for what delta G is. And that's the following. All right, the bottom line is this. The reason why it's delta G and not delta H for spontaneity is because when you have an exothermic reaction, for example, that releases this delta H, it turns out that not all of that enthalpy, that delta H, not all of that delta H is necessarily released to the outside world to do useful work. So when you have an exothermic reaction, it's not necessary that all of that delta H is released to the outside to do useful work. Some of that delta H actually gets stuck in the reaction, stuck in what I call the nooks and crannies of the product molecules. The amount of that energy that gets stuck is this, T times delta S. T times delta S has the units of energy. All right? What do I mean about some of the enthalpy getting stuck in the nooks and crannies of the molecules? Well, it turns out, and we're not unfortunately going to have time for this discussion, but it turns out that molecules have a way to store energy in their vibrations. Molecules vibrate. These bonds move. Molecules jiggle. Molecules rotate. That's a way in which molecules can store energy. And it's that energy that is not available to the outside system to do useful work. And so the amount of energy that's actually available to do useful work is delta S minus this T delta S, the amount that gets stuck in the products of the reaction. And so that's why delta G here is called the free energy, because it's this amount of energy that's free to do useful work. All right? Delta H, that's not necessarily all free. Delta G is free to do useful work. For example, let's look at this reaction. Hey, this is an oxidation of glucose, methane. Methane, major component of natural gas. So when you go home for dinner and you turn on your natural gas stove, this is the reaction that's going on. You're burning methane. Very exothermic reaction, minus 890 kilojoules per mole. This is the energy that you're going to use to heat up the water, to boil the water so you can cook your pasta. However, not all of this energy is going to be available to heat up that water. The amount that's going to be available is delta G. All right? So, first of all, we have to know how to calculate delta S for this reaction. Well, I'll show you how to do that in a minute. But the bottom line for this reaction is that delta S is minus 0.242 kilojoules per degree Kelvin per mole. If I put that delta S into this expression and calculate delta G, well, you can see I'm going to have a minus 890 plus some number. That's going to give me a negative number, and that negative number, that delta G, is going to be less negative than delta H. So not all of this enthalpy is available to do useful work, to heat up that water. Right? Some of that energy has gotten stuck in these internal degrees of freedom, effectively, of the product molecules. On the other hand, let's look at what your body does. It doesn't burn methane, but it burns glucose. Right? Minus 2,816 kilojoules per mole. If we go to calculate the entropy for that reaction, that entropy is positive, 0.233 kilojoules per degree Kelvin per mole. Hey, positive entropy means we increase the disorder when we go from reactants to products. Let's calculate delta G for this reaction. Okay, delta G here is this delta H minus then a positive number. We're going to get, for delta G, minus 2,885 kilojoules per mole. Hey, look at this. Delta G for this reaction is even more negative than delta H. In other words, in this case, we're going to get out, or your body gets out of the oxidation of glucose, all of the enthalpy to do useful work and then some, right? Your body's figured out how to do this. It gets even more energy out. And it does so because it's gotten that energy from these nooks and crannies of the reactant molecules, the essentially internal motions of the reactant molecules. There's more ways to store energy in the reactant molecules than there is in the product molecules, and so delta G here is even more negative than delta H. You get all that delta H out, and then you get even more because you don't have as many ways to store energy in the products as you did in the reactants. And so you got to get the energy's got to be conserved. It's going to come out, and it comes out. Delta G is more negative than delta H. Okay? So this works really well. Now, here's entropy. I told you we need to know how to calculate that. Entropy change for a chemical reaction. If you want to calculate that, you need to get to do so in this way. The entropy for a reaction is the sum of the entropies for all of the products of the reaction, but you have to multiply it by the appropriate stoichiometric number because these entropies here are per mole, minus the sum of the entropies of all of the reactants multiplied by this stoichiometric number. These entropies are actually absolute values. That's not too often happens in thermodynamics. You have an absolute value. These are absolute values. They're not deltas. Those absolute values are a result of the third law of thermodynamics, again, discussed in exquisite detail in 560. Okay, see you on Monday.